I am happy to announce the second speaker, Luca Guidi. He is an author of Hanami and a core team member of DryRB. Luca makes a huge impact on open source and somehow manages to build such an amazing stuff without working on weekends. At least a year ago, he written about that. He takes time to rest and on work days work on open source. He has a great blog. Check lucaguidi.com, from which I know that he's learning how to do techno music, meditating, and by the way, using OKRs to track both professional and personal goals. Luca, by the way, I'm the fan of OKRs as well. I use this approach for my personal and professional goals as well. Luca is a speaker on many conferences, but confessed this year that he saw Matt in Paris for the first time this February. Oh, for so many years working with Ruby. PWRX story with Luca started back in 2016, yeah. Then we had our meetup dedicated to Hanami. Actually, it was Lotus back then, as I remember, and Luca was so awesome to make us a personal video. So tonight, the Hanami team recently announced Hanami API, a minimal, extremely fast and lightweighted Ruby framework. Let's have a look what's inside, together with a family man, a software engineer, an open source contributor, and our special guest from Rome, Luca Guidi. Woohoo! Woohoo! And let's vote again. We have one more vote for Luca. Bum, bum. So, guys, you see one more vote poll for you. Which web framework are you using? You can do multiple choice. And do you have any experience using Hanami? Let's help Luca to understand the audience. Luca, I'm putting myself on mute and it's your turn.
I have to say this was the best presentation ever. Thank you, Anna. Really honored, and thank you, folks, for having me. I want to talk about Hanami API. That is a small. Okay, can you see my screen, right? Okay, thank you. It's a micro framework that I want to introduce today. But first thing first, my name is Luca Guidi. Anna already mentioned my website. This is my GitHub handle and my website. And I work remotely from Rome as a Toptal backend architect. And today I want to, before to start, I want to explain why Hanami API. It's basically two main reasons behind that. The first one is that we are in the process of rewriting most parts of Hanami. And one of those parts is the router. The old 1.0 version is based on an old and unmaintained library, so I had to rewrite it. And the first rewrite was out more than a year ago, and it's the first alpha of the 2.0. And then I compared with the benchmarks, and Jeremy, which is here today, helped me to discover how poor performant was that version. So I did another rewrite, and that is the result of a much better performance. So thanks, Jeremy, for helping me spot those problems. And I realized that this is something awesome, given the performance that the community can benefit of, because Hanami and the other open source projects that I work on, Dry and sometimes ROM, are meant to build libraries for the entire Ruby community, not just a walled garden, let's say. So I said, okay, how Hanami router can be reused by other people? But usually when you look into a router, you basically are there because you need to build something that is low level, So I said, okay, let's wrap it into a DSL so people can have a ready product that you install a gem, you write a file, and you have your really small and focused HTTP endpoint. So that was the main reasoning behind Hanami API. And the second thing is about low-risk Hanami adoption. That means I understand that the Hanami is a huge framework and there is a business risk and the companies are not willing to switch or to adopt it if you think about how Rails is popular in our community. But if you have something that is a very, very low friction to adopt and with a much, much lower barrier of the adoption, again, it's one gem for a small endpoint, a small service that you may have for your company, then the risk of adopting Hanami, understanding the philosophy, and from there maybe discover other parts of it or other libraries that can play well with it is a nice way to get into those companies. So those are the two reasons why I decided to wrap it up, this gem. DSL, so you have something that is ready to go, and low risk Hanami adoption. Now, let's have a look at the syntax. It's just described here in this slide. Basically, you have these gem to require. You have a superclass, just something like this. You inherit from it, and you define routes. Now you have two ways to define routes. The first one is the classic Hanami 1, that is at the line 13. You define the HTTP verb, the relative path, and then you pass anything that is a rack endpoint. It could be an Hanami action, it could be a Rails action, it could be whatever speaks rack, basically. And there is the new addition here, which is the line 9 to 11, that I believe you are familiar with, that is inspired by Sinatra. I call it the block syntax. And then you have another couple of nice features. The line 14, you can mount any rack application. Could be Rhoda, could be Sinatra, and everything that, every time that a request starts with a /dashboard, then everything is routed down to that application, and then it's that application business to fulfill the request. And then there is another nice feature, in my opinion, the scope. It acts as a prefix for the routes, so everything that is defined inside that block, it gets prefixed, for instance, in our example with a /API, and then you can have nested scopes to group together parts of your app and not repeat the prefix. But it's not just that. You can scope the rack middleware inside of it. So if you look at line 7, where there is this rack middleware, it's used by the entire app. But because the my authentication rack middleware it's at line 17, it's inside that scope, then only the requests that are targeting the API will use it, and you can nest it how many levels you want to see. This resembles the, I don't know, variables visibility, let's say. So the nested is the usage of the middleware. Only that small part of your app will use it. Okay, and as last line and last comment on the code, line 23, you see you instantiate the object that is like any other Hanami gem. You have objects, you instantiate it, and you do what you need to do, and that's very it. So the features that this micro framework exposes are just on this slide. Params, only for getting params that are from the request. Then getters and setters for status, headers, and body. So you have the three components of a response. And you have halting, if you want to stop the execution, redirect, built-in JSON rendering, scopes that are the prefixes that I've showed in the previous slide, mounted apps, again, you can mount any rack application there, and rack middleware support within those scopes. That's very it on purpose, because I wanted to provide simplicity and not try to bloat the framework with a lot of more features. So you have the very bare minimum amount of stuff that you need to get started, and then in seconding the Hanami philosophy, you can start plugging. You have full control on it. You can start plugging libraries as you need. But for now, it's very, very focused. It's only what you see here on this slide. So let's now talk about the performance. Again, this is rewriting oriented to performance. And I've used the Jeremy benchmark to as a metric to get the performance better here. So for those who are not familiar with it, Jeremy wrote a great benchmark tool that's called, sorry, I call it R10K. It's basically a way to compare Ruby frameworks, and it generates apps with 10,000 routes, and it measures a few metrics, a few simple metrics. The first one that you see here is about memory, and of course, the less memory a framework, an app takes, the better, because that means it's lightweight, right? And so Rhoda is the winner here. Hanami API is the second, and as you go on the right side of this slide, you see the other framework. Again, 10,000 routes loaded in memory without any requests happening here. You get 47 megabytes for Rhoda, 53 for Hanami, and so on. You get the idea. The other benchmark that Jeremy wrote is about fulfilling requests. So you have still the app with 10,000 routes, and the benchmark executes 20,000 requests, hitting the last route. Why the last route? Because we want to measure here the worst case scenario, right? And so here there is no problem on this slide. Actually, it's because we have outliers on the right side. For instance, to complete these benchmarks, Sinfeld and Sinatra take 3 minutes. But if we remove, and Rails 17 seconds, if we remove just the right side of the slide and we zoom in on the left side, you can see the better performing frameworks. Again, on the left side, for ease of the listener here, I put the best performant framework, and there you can, as the time to complete the benchmark increases, then you have a degradation of the performance. But here we on this slide we are having just winners here that have amazing results. So the bottom line here of this part is that competition is healthy for Ruby ecosystem. If you consider Rails for large web apps and Sinatra for small HTTP endpoint, then you may miss a point, in my opinion, because here I've discovered something that this benchmark was built, I believe, mainly to measure Rhoda performance, and then I've got somehow the push to build something more performance. So as a result, you have a really great ecosystem of very performant HTTP frameworks, and that is only because people are not accepting that Rails and Sinatra can be the only two alternatives here. So that is the takeaway for this part. Now let's have a look at the implementation, not diving into code here. But before that, I want to explain just a few performance improvements. But before doing that, I want to quickly explain this part here. So, but instead of doing boring stuff, let me explain with a game that I believe people are familiar with. Guess who, right? You have 24. I counted just before to join the conference. You have 24 characters, and you need to find the right one, right? Let's say the right one is the blonde woman here on the right side, on the back on the back of the board game. And let's say you need to find her, right? And O of n, that means basically you go through all the characters, and the last one, we are still measuring here the worst case scenario because we want to understand how our algorithm of search performs under the worst case. So to understand how good is our algorithm, let's say, so we scroll through, we go through all the scan through all the characters, and then finally we find the character that we are looking for. And this, of course, simplifying things here is O of n. You go through all of them. So the bigger is my data set, the bigger it will take time to complete, right? The second option here, again, I'm simplifying things. You start ask questions. Is he, or is a woman, or he's a man, or is she blonde, wears a hat, and so on. So in that case, you don't need to scan through the entire set of characters. So you are start decoupling the size of your data set from your for the time to complete. And this is kind of better on the previous one. But what we are looking for here is O01. That's constant time. That means I know exactly where to find the character. I know it's last row, last character on the right, so I don't need to scan through anything. I just go there and pick. One example in Ruby land is hash. When you use hash.fetch, it doesn't matter if your hash has just one element or 100, the time that you get there to get that element is constant. Now, why I'm telling you this? First enhancement here that I applied, I changed the data set. Sorry, not the data set, the data structure here, and that led to better performance. Before, I used it to store the routes inside a collection, and that is O of n. Because if I have 1,000 routes and I need to search for the last one, then I need to scan through all of them to find my last one. And this is not efficient, as you may guess. So having in a tree basically helps getting to the exact route without the need of scanning through the entire dataset that I have. So just switching to a different data structure helps to get better performance. But it's not just that. The second thing that I did, instead of having one gigantic tree inside the router, I partitioned it. And usually when you do partitioning is because you know that you can divide your dataset by a known key. And in this case, the known key is the HTTP method that a route responds to. So if I have a get request, I put into a bucket. If the developer defines a post request, I put inside another bucket. And all those buckets contain a tree. So basically, again, instead of having one gigantic tree to look into, I just separate in different partitions to have several trees. And that, of course, helps in performance because we have seen that tree is faster than an array, but if you have a smaller and smaller data set to scan through, then you basically have a gain in performance time. So to visually understand this, instead of having one tree here, you have several buckets, several partitions for get routes, post routes, put routes, and so on, okay? The third enhancement is fixed versus variable paths. I call variable path the one that has a variable in it, which is a column with an alphanumeric identifier. So at the runtime, those are less performant because at the runtime, I need to scan through my variable paths and try to match, okay? Instead, if I have a fixed route like /dashboard, I know where exactly to look for. This is 001, like we have seen before on Guess Who game. And fixed paths have their own bucket in my partitioning. So to visualize this, as before, we have those trees and then have another bucket for fixed paths. And inside those fixed paths, if we zoom in the last box here, there are other partitions. So the bottom line here is that separating the data structure, I understood that the tree is performant, but having smaller trees where I can know exactly where to find things, it's good. Imagine you have a bookshelf and you separate your books per topic. It's much faster if you need to find Japanese recipes rather than, scanning through the entire library. That's it. That's it applied to HTTP routing. Now, if this looks complex, in the end, what it does here, I believe that you cannot, everybody here can understand with a basic knowledge of Ruby. This is basically the data structure for the fixed routes. You have the main partitioning key, that is the get, the post, that means the HTTP verb, and then you have the key, the fixed path, dashboard, books, whatever, assigned to an endpoint, and at the runtime does this. It does dig the request method, again, because I need to understand which bucket have to look into, and then the path. And it may return an endpoint or nil. If it's nil, then I start to scan the variables, because that requires much more computation, means, again, trying to match with the regular expressions, the variables in a path. And just to wrap up this section here, the first route gets in its own bucket, the second one has a separate bucket, and the third one has a separate one. So this explains the several partitioning techniques. The other thing that I want to talk about, two more things. Micro speeds enhancements. I'm obsessed by performance, and I used to run snippets of code with benchmark VM. So I run a lot of time when I get my test passing, trying to compare several snippets and decide which one is performing faster. So I do this kind of benchmark. And for instance, the takeaways for my experience here, instance variables are faster than getters. This syntax is faster than unless full nil. Avoid each with object. Those are my takeaways for my experience with Hanami API. My suggestion here is to always benchmark your code, not take my word for granted. And the last one that I want to talk about, keep dependencies. The less gems you have, the better. I literally copied stuff from Hanami Utils, which is a utility library that is shared across all the Hanami gems. Here, for the sake of not overwhelming people with a lot of dependencies, I just literally copy and pasted some snippet, some code that I needed there, here. But the result is 600 lines of code, the router, and 200 lines of code, the Hanami API. So it's very, very lightweight. And if I do this is the very last thing that I want to talk about. This is getting back to the benchmark of before. This is the before and the after I applied those techniques. Those are still the benchmarks that we have seen on before. So you can see it took more than 2 minutes to complete the benchmark on before, and now less than a second. And 7 seconds to start, now 1 millisecond, and less memory occupied. So as a conclusion here, I just want to reply to people that always ask, is Ruby worth to be learned, or is Ruby bad in 2020? I always answer with this: the present of Ruby is bright and the future is exciting. Thank you, everybody.
Thank you, Luca. Mohdan, it's your turn to ask the questions.
Yep.
Keep an eye on answered one. There is a top actually one, I think he has 11.
Yeah, thank you for such a great talk, and thank you for supporting Hanami since Lotus and since 2014, 15. And the first question would be Hanami versus Roda. In which use cases would you recommend to use Hanami, and in which would you recommend to use Roda?
I assume that you are talking about Hanami API, right?
Yep.
I mean, they are equivalent in my opinion. Maybe Jeremy disagrees, but they are covering basically the same market share if you want. Roda may have much more features that I decided to keep out on purpose. So just my suggestion here is not to listen to me and listen to Jeremy. Just install those two gems, read the documentation, understand what fits your use case, and then pick one.
Okay, thank you for that answer. And the next question would be, Hanami API is great, but what about the cases when I need only one endpoint for GraphQL application, for example? Do I really need the whole framework for that?
Really, if you consider that you need only one endpoint, then maybe you can just go through something really homemade. But don't forget that you can plug into, I mean, Hanami API has some facilities like params and JSON parsing or body parsers that you need to build by your own, because Rack only sends to you the stuff, the params that are in the URL. Anything else needs to be parsed. So that is a facility that you can have for free by using Hanami API. And the other thing is that you can plug their Hanami actions that have much more advanced features there. So you can have just one Hanami action to, if you need to do a lot of authentication stuff, a lot of let's say mundane work before to pass it through the GraphQL schema. So I believe that going by your own, it's viable, but you may hit a wall soon. But here you have already things already implemented, and both the router and the actions are used. I mean, the previous versions, but we didn't. The core of it is staying there. We are using it. Used it at previous job for years in production. Now we changed things here and there for the actions, but they are battle tested. So my suggestion is to leverage that production world experience rather than going by your own. But the choice is yours, really.
Thank you. And thank you for your beautiful presentation.